All right, the purpose of this video is to go through some more difficult U substitution problems, particularly ones where it's difficult to tell which form to try to match. Before watching this video, you should for sure have completed U substitution 1. There's about 20 problems on that sheet that you should be 100% comfortable with. Make sure we're good doing the process of U substitution in order to succeed with the stuff in this video. All right, so there are 4 forms that we're going to focus on in this video. There are 11 integration forms that we're covering in this as part of this course. There are 4 here, two sets of which look a lot alike. And so I want to look at the form 1 over u du versus the form 1 over 1 plus u squared du. So these are the first 2, and then we'll do 2 that are similar to this here in a few minutes. When you glance at these, the reason they're similar for U substitution is because when you have a fraction in the original integral, U could be set to equal the entire denominator, and so U could have addition within it. And then if you have one like the one on the right, U could be the square root of part of the denominator. And so there are problems that look similar to each other, and some of them are done using the first form, some are done the second form, some neither of these forms would work. And so we want to try to distinguish between those. So let's look, for instance, at this problem. So let's say I have 5x cubed over 6x to the 4th plus 7. Okay, so when we're doing this problem, the 7 makes it a little bit different from the second problem, but there are manipulations you can do where the 7 in the bottom could end up becoming a 1, and we'll see those in a minute. But either one of these 2 forms are legitimate approaches. The first approach we should maybe attempt is we should try to let u equal 6x to the 4th plus 7, thinking that we're going to match the first form. So I want you to think for a second, pause the video and decide, is this approach going to work on this first problem or is it not? Okay, this is going to work, and the reason why is because the derivative of this is 24x cubed, so du is 24x cubed dx, which means we have the part of the du that we need. So we can quickly pull the 5 out. We can rewrite the fraction as 1 over 6x to the 4th plus 7, and then we put the x cubed next to the dx. That gets us 5 integral, we're going to want to do 24 and 1 over 24. So we're going to do 5 times 1 over 24 times the integral 1 over 6x to the 4th plus 7, and then we put a 24 next to the x cubed. That gets us 5 over 24 integral 1 over u du. That gets us 5 over 24 integral log of the absolute value of u plus c. And then that's 5 over 24 log of 6x to the 4th plus 7 plus c. It would be okay if you had absolute value. You don't need to put it here because the x to the 4th is always positive, so or 0, and so then the argument there, the inside of the log, is always positive. Okay, so this one, the log form works. I want to look at another one. So problem 2. Let's say we've got 1 over, we'll do 9 plus 16x squared dx. Okay. So when we look at this problem, the first thought should be probably that we're going to try to match the 1 over u du form. If we do that, u is 9 plus 16x squared. Du then is 32x. The problem with that is that there's no x in the numerator, and so we're not able to get the du that we need in this case. So what we could try to do is try to match the second form, and it's going to work here, but the biggest difference between problem 2 and the form on the top right of your screen, the 1 over 1 plus u squared du, is that you have a 9 rather than a 1. So what we do to kind of fix that is we factor a 9 out. Because it's on the bottom, we pull it out as a 1/9, and then we get 1 over 1 plus 16/9 x squared dx. And so the reason that works the way it does is because if I were to distribute the 1/9 through, the 9 would go to the bottom, and I would get 9 plus 16x squared. Now, that matches the form on the top right almost exactly. In fact, it matches it exactly if we let u equal 4/3 x. Now, I'll tell you why we pick that, but I want you to pause the video and see if you can determine why we pick u to equal that first. Okay, so we pick u to equal that because if we square that, then 4/3 x, if we square all of that, is 16/9 x squared. So then the bottom is 1 plus u squared. So u is 4/3 x, du then is 4/3 dx because it's the derivative of that. So I can get that at the end by multiplying inside by 4/3 and outside by the reciprocal of 4/3, which is 3/4. That then gets me the 3 and the 9 canceling, so we get 1 over 12 outside. But now this is 1 over 1 plus u squared du, and now that's inverse tangent. So we get 1/12 inverse tangent of 4x over 3 plus c. And that's the answer on this problem. Okay, I want to look at another problem similar to that. And so let's look at the integral of 5x over 9x to the 4th plus 25. Okay, so if we have this problem, again, it looks like the two forms at the top of the screen, 1 over u du and 1 over 1 plus u squared du. I think the easiest approach is to start by attempting 1 over u du, and at least attempting that in your head. And so the way we can think of this informally is if we try to match 1 over u is the entire denominator. So u would be 9x to the 4th plus 25, which means u is basically x to the 4th. The derivative of that, du, would then be 36x to the 3rd, but basically x to the 3rd power. Unfortunately, x to the 3rd is not the variable part that we have in the numerator, so it's difficult or impossible to use the first form. So then the other option is to try to match 1 over 1 plus u squared. And let's see how that works here. And so we're going to do something similar to what we did on the first problem. I'm going to pull the 5 out from the top because we won't need that. I'm going to pull the 25 out from the bottom. And then that's going to leave 1 plus 9/25 x to the 4th on the inside in the denominator. And again, you can check that that's right, because if you distribute the 5 over 25, the 5 would go to the top, the 25 would go to the bottom, and we would get 25 plus 9x to the 4th, which is just the reverse sum. Okay, now, for this to match 1 over 1 plus u squared, u has to be whatever you square to get 9/25 x to the 4th. Well, to get that, you square 3/5 x squared. So then du is 6/5 x dx. And again, the reason u is 3/5 x squared is because if we square that, 3/5 squared is 9 over 25. X squared squared, you multiply powers, so x squared squared is x to the 4th. So we now try to get this to work out. So the 5 over 25, we simplify to 1/5. We move the x off of the fraction. We need a 6/5 inside. So we multiply inside by 6 over 5 and outside by 5 over 6. The 5's cancel on the next step, so we get 1/6. This is 1 over 1 plus u squared. And the 6/5 x dx is du. That's now the form that we want. So we get 1/6 inverse tangent of u plus c. That's 1/6 inverse tangent of 3x squared over 5 plus c. Okay, so it's important to be able to look at these and determine which method to use first, or which method to use that'll work on the problem. And so if we look back at the first problem, the log form worked. And the reason the log form worked is because u equaling the entire bottom meant that u was basically x to the 4. Du then is basically x to the 3, which is sitting on top. That doesn't work on problem 2 because if u is the entire bottom, u would basically be x squared. Du would basically be x, which is not on top. For inverse tangent to work, u is the square root of the variable part. So on problem 2, u for that, before we even did the problem, we could have looked at that and realized that u would basically be x to the first if we were going to use inverse tangent. If u is x to the first, du is some constant, which is what is on top, and that's why we would know that would work. On problem 3, if you're looking at it and not sure how to start, you would look at problem 3 and say, okay, if u is the entire bottom, u is basically x to the 4. Du then is basically x to the 3, which is not on top, so that would not work. If we're going to use inverse tangent, u would be the square root of the variable part, which would be x squared. Du then would be basically x, which is on top. That means we know it's going to work. So what I want to do one more problem, but I'm going to put 3 on the screen. And what I want you to do once I get these 3 problems on the screen is I want you to pause the video and I want you to write which one of them is log, one of them is going to be inverse tangent, and one of them neither approach works. And so I want you to figure out without doing any work which one is log, which one neither approach works on, and which one is inverse tangent. And so let me put these 3 problems up and then we're going to do the inverse tangent one. So let's say I've got 7. Oops. Okay, so again, pause the video, figure out which of these, that's a 12 at the end there, figure out which of these is inverse tangent, which of these is natural log, and which of these neither form works. Pause it, put down what you think, and then fix it in a minute if you're wrong. Okay, so looking at these 3 problems, the denominator is the same on all of them. So if we're going to match log, u would need to equal the entire denominator, which would mean u would be basically x to the 12. Du then would be basically x to the 11. It'd be a constant times x to the 11, but basically x to the 11, which would mean that we can use the log form on the first problem. And it's equally important that you cannot use the log form that way on the second 2 versions of the problem. For inverse tangent, we would need u to be the square root of the variable part. We'd have to factor out the 16 and the constant would change, but the variable part would be the square root of that, which is x to the 6. So for inverse tangent, u would be x to the 6, which means du would be x to the 5. That means that inverse tangent, or arctangent, works on the second problem and neither form works well on the third problem. So let's work through the second problem and see, just to get some more practice on that, and then we'll talk about a couple of other forms. So we've got 7x to the 5th over 9x squared plus 6, or I'm sorry, 9x to the 12th plus 16. This will be the next problem we actually work out. Okay, so again, if we hadn't said what to do to begin with, first thought should be let u equal the entire bottom. Du then would be a constant times x to the 11. That's not going to work well. So then what we want to do is try to match inverse tangent, because then u would basically be x to the 6. Du would be basically x to the 5, which is what's sitting on top for us. So to match inverse tangent, we need the constant on the bottom to be a 1. So we factor out the 7 from the top and the 16 from the bottom, and we get 1 plus 9/16 x to the 12th on the bottom. U is then the square root of that second term, which is 3/4 x to the 6th. It's what you square to get 9/16 x to the 12th. Du then is 18/4 or 9/2 x to the 5 dx. So now we need the 9/2 x to the 5th at the end of the problem. We move the x to the 5th off the fraction. We put 9/2 here, which means we need 2/9 outside. That gets us 7 over 72, integral 1 over 1 plus u squared du. That's then 7 over 72, inverse tangent of u plus c, but u is 3/4 x to the 6th. And so that is our answer on this problem. Okay, a similar relationship exists between these two forms. So on the ones above, we had 1 over u versus 1 over 1 plus u squared. This form and this form, depending on what we set up as u, can look basically the same. The one on the left is technically not a basic form, but you can immediately rewrite it as u to the -1/2 to make it a basic form. And so a similar thought process occurs as to which one works. So if I'm doing this problem, let's do. Okay, so if I have x to the 7th over the square root of 25 minus 9x to the 8th, then again, the two forms that it basically resembles are 1 over the square root of u and 1 over the square root of 1 minus u squared. So the first thought is, let's try to do 1 over the square root of u. If we do that, u is going to be the entire inside of the square root, which is 25 minus 9x to the 8th. Du then is -72 x to the 7th, which means this will work because the x to the 7th is sitting in the numerator. So we rewrite the problem as 1 over the square root of 25 minus 9x to the 8th. We move the x to the 7th off the fraction. We put a -72 inside and a 1 over -72 outside. That gets us -1 over 72 integral 1 over the square root of u du. That gets us -1 over 72 u to the -1/2 du. Now we apply the power rule. So we add 1 to the power. -1/2 plus 1 is +1/2. So we get negative 1 over 72 times 2 times u to the 1/2 plus c. That's negative 1 over 36 times 25 minus 9x to the 8th to the 1/2 plus c. If we wanted to rewrite the 1/2 power as a square root, we could, or we can leave the answer like this. Okay, that's a little harder than the log form, but it's the same thought process where u is the entire inside of the square root, like on the log form, u is the entire denominator. If we have the same denominator here, what I would like to do is a problem where this is the denominator and we end up using the inverse sine form, the square root of 1 over the square root of 1 minus u squared. So if you can think about it for a second, pause the video and put in the numerator the variable part that I'm going to put there so that this will work. So see if you can make up the problem so that that second form will work. Okay, so x cubed is what ends up working, and the reason we can know that is because if you see this problem to begin with, probably the first thought should be u equals 25 minus 9x to the 8th. du then is negative 72x to the 7, which won't work well here. So then the other option would be we can mess with this to make the 25 become a 1. Once we do that, u is going to be whatever you square to get x to the 8. So u is basically going to be x to the 4. It'll be a constant times x to the 4. du then is another constant times x to the 3, which means this will work. So we have to make it so that there's a 1 at the beginning of the square root. So we pull out the square root of 25 and make this the square root of 1 minus 9 over 25 x to the 8th. Now u is going to be what you square to get that variable part. So it's 3/5 x to the 4th, because if you square 3/5, you get 9 over 25. If you square x to the 4th, you double the power, which gets you x to the 8th. du then is the derivative of that, which is 12/5 x to the 3rd dx. So we do a few things on this next step. The 1 over square root of 25, we go ahead and write that as 1 over 5. We're going to take the x cubed off of the fraction, and we're going to put the x cubed next to the dx. We need 12 over 5 there. So we put 5 over 12 outside. That gets us 1/12 integral 1 over the square root 1 minus u squared du. The integral of that is inverse sine of u plus c. So our final answer is 1/12 inverse sine of 3x to the 4th over 5 plus c. Okay, so the problems in this video are technically not any more calculus intensive than what we were doing in the first set of U-sub, but the algebra and the manipulations are a lot more intensive. So at this point, you should work on the problem set called U-substitution 2. There's a lot of problems that match these forms where we're trying to use log or inverse tangent, and then other problems where we're trying to use 1 over the square root of u or 1 over the square root of 1 minus u squared, which is then inverse sine. All right, thanks for watching this video. Let me know if you have any questions.